Hello everybody, welcome back. Today's lecture is all about answering this question, what is a sampling distribution? Now this follows chapter 7.1 in our textbook. Let's get to it by looking at our essential question. We want to know today, why are sampling distributions important in the study of statistics? Let's refresh our ideas what statistics is. A major goal in statistics is to make an inference about a population, because it's hard to measure everyone in a population to get the truth. What is truth? The truth is called a parameter. It's some number that describes a characteristic of an entire population. But because that's really difficult to do, to go out and measure every single individual, we instead get lazy and we only take a sample from the population. Now the information we get from that sample, that's what's called a statistic. And it's simply a number that describes a characteristic of that sample. Well, that should beg the question, how do we know if that sample really speaks well for the entire population? Let's try and explore this by taking a look at puppies. Imagine a certain breed of puppies. Now you want to determine the average weight of a puppy of this breed. How can you do it? Let's look at all the puppies. That would be looking at a population distribution. Just all the puppies, and we measure the weight of every single one of them. So this is a population distribution. We should remember this from chapter 1. It describes a characteristic of all the puppies, every individual in a population. Now, what is the average weight of these puppies? To be honest, I really don't know. That's a lot of puppies. I'm not going to be able to even get a hold of all of them, right? The population distribution is hard to actually look at. Well, could you guess? I suppose we could just take a random sample of, say, 5 puppies. I can end up finding 5 puppies, and then we get the average weight, X bar, from each one of those. So, in just a small sample of puppies, we are looking at a distribution of sample data. Now, the distribution of sample data is describing a characteristic of just some of the individuals in the population, and in this case, just 5 puppies. Because we have lowercase n equals 5, again, that tells us that's our sample size equals 5. Now the average of this distribution is noted with the symbol X bar, and in this sample we can see that the average is going to be 15 pounds. You're just going to have to trust me, I did the math behind the scenes on this one. Well, this is going to also beg the question, is this a reliable estimate? Well, random variation says maybe not. We know that any one sample is going to vary from the next when they're chosen at random. Also, any one puppy is going to vary from the next one at random. So just due by random chance, maybe these puppies are a little overweight, or maybe they're a little underweight. I'm not sure. So what should you do? Let's look at more puppies. So we get another small sample of puppies, another distribution of sample data. You see them right on top of each other. Sample 1 hasn't changed. That's still the X bar with 15. But now we have a second sample. And we notice that in the second sample, also with sample size 5, that's important, that this sample, they tend to be a little heavier. So in the first sample, we had an X bar of 15 pounds, and in the second sample, we had an X bar of 23.2 pounds. So which is the better estimate for the true mean weight of this breed? I don't know. I don't know anything about puppies. I'm actually more of a cat person, so I couldn't tell you if these puppies are big or small or what. So what should you do? Let's look at a lot more puppies. Actually, we're going to cheat just a little bit. We're not going to keep looking at more and more and more puppies. The idea is that that's too time consuming, so we want to try and make this a little less work for ourselves. So how are we going to cheat? We're going to look at this thing called a distribution of sample means. Now, as you can see, all the puppies are gone from our dot plot and they've been replaced by X bars, sample means. So that's what a distribution of sample means will look like. Each dot is going to represent a mean from a different sample. In this case, our first mean, X bar sub 1, was 15 pounds. You see it on the x-axis there. And then the second one, just shy of 25 pounds, was our second sample average at 23.2 pounds. Well, why is this going to help us? Well, if we took the average of 5 puppies twice, why can't we take the average of these? You say, wait, take the average of averages? Well, yeah, actually, this is going to be exactly the same as if we were to combine all of these puppies together in the same sample and take the average. We can just take the average of their averages. When we do that, 15 plus 23.2 divided by 2 for the number of averages we had, we get 19.1 pounds. And what's special about this? Well, it split the difference between those two samples. What was those differences accounted for? It was probably just due to random variation, but it may have been due to outliers. So this also minimized the influence of those outlier puppies when we take the average of all of these samples at the same time. You say, okay, so now what? Does that mean that the true mean weight of puppies of this breed are 19.1 pounds? Maybe. We're getting closer. How we get even more close is by looking at the sampling distribution of sample means. So what is this sampling distribution of sample means? How is it different than the thing we just looked at? Well, we're not just going to look at two sample means. We're going to look at dozens, hundreds, thousands of sample means over and over and over again, many samples. And what we can see here in this sampling distribution is that each dot is going to not represent one individual puppy. It's going to represent a mean from a sample. It's made up of countless X bars. Now, a true sampling distribution is actually made up of all possible samples of the same size. And in this case, that means the sampling distribution is made up of the sample average weight of all possible samples of 5 puppies. So that's a lot of averages that we could be looking at. Well, what's special about this? Well, sampling distributions happen to be very predictable. So some characteristics of sampling distributions. First, we want to take a look at the shape. This shape should look very familiar, and this is going to be true for a lot of sampling distributions because sampling distributions tend to be approximately normal. Now, that's really only true if the sample sizes were sufficiently large. How large does that need to be? Well, the rules are different for each statistic, whether we're looking at means or we're looking at proportions or something else. And we'll get more on that later as we get into the more specific details. But for right now, we just want to know they could be approximately normal. And that's going to be really important because that's going to help us see how these things are predictable and how they can behave. If we understand how they behave, then we can start to calculate probabilities, start to see how unusual or typical one particular sample is from the next. It means we get to revisit our old friend Norm CDF. You got it. Now, what else? Now, the second characteristic is probably the most important one about sampling distributions. It's going to be a huge help for us throughout our inference in the next couple of weeks, and that is that sampling distributions tend to provide unbiased estimators. What does that mean? It means the average of the sampling distribution will tend to be the same value as the parameter you were trying to estimate in the first place. Now, we note this by using the symbol mu sub x bar to represent the average of the sample means, and in true sampling distributions, mu sub x bar is equal to mu. Now, I say approximately here because a lot of times we might be looking at not true sampling distributions. We might be looking at just very large sampling distributions, but not true ones. So you can always just utilize this as a guide, saying that they are going to be the same. On average, in theory, the average of the sampling distribution is the exact same as the parameter you were trying to estimate. And that is a big deal. Why? Why is that a big deal? Because it gives us empirical evidence that the average of all of our samples will be the same as the population parameter, the thing we're trying to estimate. It tells us unequivocally that our samples will generally represent our population, and that is a huge deal. Well, why were our samples different then? We saw two samples that were pretty different from our population. Why were the original samples so far off from the true mean when we looked at our first 2 puppies? Well, that had a lot to do with sample size variability. In our original sample, we only had 5 puppies in each one of those samples, and small sample sizes tend to increase variability. You can see that by the sampling distribution you see on the left. It's pretty wide, it's got a pretty fat base. But if we look at the sampling distribution on the right, where each one of these X bars represents a sample average of 100 puppies. So every single time we took a sample, we looked at not 5 puppies, but 100 puppies at a time. And what do we notice about this? 2 things. First, they have the exact same center. They're located in the same place in the graph. However, the one on the right is much more reliable. They were consistently closer to that center than the sampling distribution with the smaller sample size. So that's a big deal. Now, that brings us up to three big characteristics about sampling distributions that we want to make sure we remember. First, that sampling distributions will tend to be approximately normal. Second, the center of that sampling distribution will be the same as the population parameter. And third, larger sample sizes will decrease sampling variability and make each one of our samples much more reliable. Now, before we close out today, let's make sure we have some fun with notation. We talked about three different distributions and three different sets of notation. Let's make sure we've got them all down. Let's write them in the left-hand column. First, we looked at a population distribution. This describes a parameter. Now, the two big ones that we're going to be talking about, two big characteristics or parameters that we are going to look at are the population mean and the population proportion. For those, we use mu and p. And we look at these two because they're going to be our primary characteristics in describing either quantitative measurements, we'll use mean, or categorical measurements, in which we'll use proportion. Then we talked about distributions of sample data, where we just looked at 5 puppies at a time, and we knew those describe a sample. Now today we looked at X bar for the sample mean, but we will also look at categorical data for sample proportions, in which the symbol we use there is p hat. Then finally, we talked about the sampling distribution. Now, there's a lot more notation that goes into this for today, but what we want to first remember is that a sampling distribution is going to describe a statistic from a sample, and we are going to focus right now on just the center. The average of the sampling distribution, the sample mean, is mu sub x bar, and the average of the sampling distribution of the sample proportion is going to be mu sub p hat, and we will get more practice with writing out this notation and applying it. That is going to bring our lesson for today to a close, and now we can finally answer this question: why are sampling distributions important in the study of statistics? Well, sampling distributions help us with inference because they are going to show us how samples in general behave. Now, that's important to note. We don't really want to create sampling distributions. I'm not going to ask you to make them. That's incredibly difficult, if not impossible, to do. But we want to know how they behave. And the math theory behind it tells us that we can know how they behave. And if we know how they behave, that allows us to know if samples will give unbiased and reliable estimates. And that is exactly what we want to do in statistics. All right, that does it for today's lesson. Thank you guys for watching. See you in class next time.